Thanks for having me. I'm going to be talking about work that I did with Jeffrey Simpson, Sarah Martel, Grant Lewis, and a bunch of people in the GLOC collaboration. We've all seen this wonderful image from Gaia. So this is going to be work that involves Gaia data. Okay, it's not advancing. There we go. Okay, so as we've all seen, and as we've probably all heard, Gaia parallaxes and astrometry have really revolutionized what we can do in terms of finding stellar structures and substructure in the Milky Way and around the Milky Way. But trying to figure out what the substructure is really requires abundances for the member stars. So abundances, for the most part, and I know people will be quibbling about this, but for the most part, abundances remain constant over the lifetime of the star. And they tell us about the conditions in which the stars form. For example, did the stars form in a dwarf galaxy? What was the mass of the progenitor object? What was the time of the latest star formation, which gives kind of an upper limit for when the object was accreted, if it was accreted, in fact. So how can we find the stellar evidence of mergers and accretion? Or rather, how can we distinguish accreted stars from the ones that formed in situ in the Milky Way? Now, for much greater detail and in the analysis, you should look at the talks by Sven Buder, Emily Cunningham, and Brower, Kaylee, thank you, Kaylee Brower on chemical tagging of accreted stars that were on yesterday. Apologies. So stars may be clustered spatially. They should be clustered in orbital parameters. Stellar age distribution should be truncated at the time of accretion. We don't expect accreted objects to continue forming stars once the Milky Way is gobbling them up. And the stellar abundance pattern should tell us something about the environment in which the stars formed. So what do we expect, for example, dwarf galaxy stars to look like? And again, this has been kind of covered, but the main gist of it, I would say, is that stars that formed in dwarf galaxies typically have lower, at relatively low Fe on H, they tend to have relatively low alpha to Fe relative to the thick disk of the Milky Way. And you see this with empirical data down here with a Venn diagram. And also, just to differentiate them from, say, globular clusters, dwarf galaxies also typically show a range in Fe on H. An example of a structure that was found, sorry, one slide has advanced and the other has not. There we go. There's a lag, yay. So the Gaia Enceladus sausage, we've heard quite a bit about it, but just a quick recap, it was identified essentially kinematically. You can see here from the Helmy paper, and here's also from the Bullock paper. Bullock called it sausage, Helmy called it Gaia Enceladus. But if you look at the alpha to Fe versus Fe on H, you notice that the bulk of the stars are actually lower alpha Fe at a given Fe on H, lower than the thick disk, which does strongly point to it being from a dwarf galaxy. Now, a really interesting paper came out last year on the NIC stellar stream. It's a prograde stellar stream that was identified using deep learning methods on Gaia DR2 data. And the kinematics were distinct from the stellar disk of the Milky Way. Basically, the rotation speed is lagging by 90 kilometers per second, and the stars showed a significant radial velocity. So it looked kinematically distinct. And the abundance information also seemed to indicate it was distinct. So using the magnesium to iron data from Ray-Vaughan, magnesium being an alpha element, it looked like the alpha to Fe versus Fe on H was kind of low, suggesting a dwarf galaxy remnant, that basically the stars were left over from a dwarf galaxy that had been accreted. Now, one of the strange things about it, of course, was that the Fe on H, the mean Fe on H, was around minus 0.5, which is pretty high. I mean, for example, Gaia Enceladus, a major accretion event, is around minus 1.5. And if you look at this plot from Kirby looking at the dwarf galaxies, I mean, minus 0.5 is practically off the scale. You're talking like Large Magellanic Cloud. Again, looking at the luminosity metallicity relation for dwarf galaxies. So that seems a bit odd. So we took a look at it using Galax and apogee data. Sorry, there's a lag. We use the same kinematic criteria to select candidates in Galax and apogee. And in both the Galax and apogee data, which are based on high resolution spectra, the positions of these stars in the magnesium to iron versus iron to versus Fe on H plane were consistent with thick disk stars, as you see up here. The only data set that seems to indicate that these stars are low alpha Fe was the Ray-Vaughan data based on medium resolution calcium triplet data. We then went on to compare the abundances with Gaia Enceladus sausage, you see here in the black dots, in a variety of elements and element ratios. And again, Gaia Enceladus sausage, we believe, is the likely accreted dwarf galaxy. And you see that the Nix stars all appear to be consistent with thick disk and not Gaia Enceladus sausage. Looking at apogee data, which goes out much further, so you can look at more, essentially more dwarf galaxies. It's not consistent with Sagittarius. It's not consistent with the LMC. It's not consistent with Gaia Enceladus sausage. So, and it is consistent with thick disk. So basically, it looks like Nix is actually galactic disk kinematic substructure, and not the remains of a satellite, a dwarf satellite that's been accreted. I mean, it could be the result of an accretion event. It could be something that was disrupted by an accretion event or merger, but otherwise it looks like it was formed in situ, and the abundances are completely consistent with being galactic thick disk. So I may be ahead of schedule, I may be behind the schedule. Can't see the timer, that's always a downer. So the Gaia data—
3 minutes.
Sorry?
You have 3 minutes, so you can take
3 minutes, all right. I'll go slower. All right, so the Gaia data have revealed a wealth of substructure both within and around the Milky Way, as I mentioned, but it's important to really identify the nature of what you're looking at, what that substructure is. And for that, you really need the abundances for the member stars, because these tell us about the environments in which the stars formed. Tell us, was it a dwarf? Was it a, was it a globular cluster? Was it, in fact, just something in the disk that has been perturbed? Looking at the detailed stellar abundances for the Nix overdensity, we've been able to distinguish between what appears to be a purely kinematic galactic substructure and what was claimed to be the remains of a dwarf accretion event. And so if I have a bottom line, punchline, moral of the story, spectroscopic abundances are really, 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 really important for understanding any structures you identify kinematically. And I will finish early.
Cool, thank you so much, Daniel. I couldn't agree with your last bolded point anymore. Are there any questions for Daniel on Zoom? Or in the room? Just let me know if someone's asking a question in the room. I have a question. So do you have any ideas of what kind of perturbation could cause such a dramatic, radial velocity offset from the thick disk? Do you have any hypotheses about what could be going on there?
No, we didn't go into a deeper study of that. There have been, it was actually interesting. The referee pointed to some papers that there have been some possibly similar detections of substructure, like the splash detected by Blokarov et al. I think it was Blokarov et al. So I think there have been some similar kind of detections, but in terms of what sort of thing, I mean, people have written papers about, okay, if you have a satellite interacting with the Milky Way, it could have this kind of effect, but we didn't go into the details of trying to figure out exactly what sort of massive satellite, what kind of orbit would do that sort of thing. We basically just said, well, look, these stars look like they're Milky Way stars, as opposed to they came from outer space.
Cool, very cool. You also showed, a few elements are, is it does it look like a thick disk, and essentially any element that you can measure with reasonable precision, or are there elements that it maybe stands out a little bit differently?
Well, okay, so in Galah, I mean, we looked at alpha, we looked at magnesium, we looked at nickel, and we looked at sodium. And in each case, I mean, as you can see, basically the red dots are the kinematically identified NICS candidates. They all match up with thick disk stars. And these thick disk stars, I should qualify, were identified kinematically by their kinematics, not by their abundances in the Galah data, because we wanted to make sure we weren't like, going in circles. And then again, you look at the apogee and it looks pretty thick disky. I mean, there's maybe a couple of stars that look a little bit like GS, but again, with kinematic selection, it doesn't, there's going to be false positives and all that sort of thing. So I think of the elements we looked at, of the elemental ratios we looked at, there's no evidence that it's anything other than thick disk.
Cool. So Sarah Martel has put a question in the chat asking, has anyone gone back to the SDSS streams to check on their abundance consistency?
On which stream? Oh, the field of stream stuff. Oh, geez. I don't know. Well, I mean, one of the biggest ones was Sagittarius. I think everybody believes Sagittarius, right? Yeah, I mean, I think people have been following them up. They've been following up how 5 was kind of obvious where it was coming from. Orphan stream, I think there've been abundances, right? I mean, one of the issues with some of the SDSS stuff is that it's kind of faint. So you need to go with low resolution, probably calcium triplet kind of stuff, rather than high resolution. But yeah, that's that's also something that I and Sarah and so on are part of another survey called S5, and we're doing follow-up of stellar streams in the halo. And again, we're only doing low resolution, so we're using calcium triplet and low res blue, but we're still able to tell some things about the objects, about the streams and structures that we're finding.
Cool.